So hello everybody, I'm from Bischke, Germany, and I'm working for 8 years now on the field of crowd condition estimation. And in this presentation and work, I present a novel machine learning based method based on signal to noise ratio and signal phase measurements measured by compatible Wi-Fi CSI channel state information hardware. So a little bit of a background. So in previous work, in related work, we were dealing with large crowds where a high degree of signal blockage was occurring. So we did experiments all over the whole world. You will see like an example at the Oktoberfest in Munich in Germany. We also have been in Shanghai at large fairs and in other places around the world. So it was possible to use like RSSI information and algorithms to infer the crowd condition at those places. But in this work, we only have subtle influences by a small number of static people, like for example in rooms, or for example especially in shared office spaces. So in this case, more complex metric is needed than in very dense and moving crowds. So the contribution in this work are methods to estimate the fill level within shared office spaces by the exact number of people or the level of the occupancy level, depending on what is needed in different cases. We analyze different kinds of antenna setups, and we did experiment evaluations in multiple environments. So the environment is complex, so we have multiple effects going on. We have signal absorption by human bodies and structures in the room. We have reflections due to multipass. We have other physical signal wave effects like refraction, for example. So in our experiment environment, we're dealing with a shared office space where between 0 and 8 people in a varying over time, the number of people varies in this office room. Some people are doing work externally, some people are doing work in this specific office place, so the number of people changes over time. And it's important to mention that they do their regular office work. They were not instructed by us to behave specifically to our demands. It was important to make this experiment a real-life experiment. So we have like signal emitters. This is the Wi-Fi CSI access point having these 2 displaced antennas on one side. On the other side, we have a directional antenna where the signal link is straight and the people are like blocking line of sight. Then we have a second line antenna on the second row of people, and we also have an omnidirectional sensor antenna, and of course the processing unit. So basically, we have a signal phase difference available from 30 subcarriers of one single Wi-Fi band, and with those subcarriers, we can evaluate the signal phase on small windows. We use 1 second windows to measure the mean variance, minimum, maximum signal phase difference. And similar to this, we use the signal to noise ratio to measure on each of those 30 subcarriers in the Wi-Fi band in 1 second windows. So regarding 13 working days, we gathered an amount of 12.5 gigabyte of feature data, which is about 1.9 million of samples per antenna per carrier. And what is the most complex thing is like extracting the ground truth annotations. We did this with students who annotated the whole data stream with the ground truth video camera each 5 seconds. So we used 70% for training and 30% for testing. Like, as a machine learning classifier, we used a random decision tree forest, which were fastly generating the classifier model. We also tried other machine learning methods, like neural nets, for example, scalable vector machines. They resulted in similar results, but they were much slower. So, most interestingly, I will show the results. So, by using one omnidirectional sensor antenna, we got an F1 score, which is a balance between the precision and the recall. We got a score of 0.61 with just a single sensor antenna, which is not placed carefully in the room, just on one side of the room, and the emitter antennas on the other side. So with carefully placed directional sensor antennas, we nearly achieved the same result. So carefully placed antennas do not give us a significant better result than a single omnidirectional antenna. So this was an interesting result for us. But nevertheless, by combining the number of sensor antennas, by using 2 directional antennas and 1 single omnidirectional antennas, we could increase the F1 classification score to 0.67. So we used, as a baseline comparison method, we used the office occupancy statistics, which is an hourly statistics about the number of people being present. And as a comparison, we see that we have a much worse F1 score by just 0.26, which is pretty low compared to our method by estimating the exact class of the number of people. So a second approach is to not exactly classify the number of people, but to classify the range of the number of people. For some applications, it's also only interesting to know if the room is empty or really full, or it's like a state in between. So for this case, we have a F1 score of 0.87, which is for many applications a very good result, which can be used for real-life deployment. So I want to come to the conclusions, and it's a challenging problem with only those subtle signal variations by those mostly static and sitting people in an office room. So in related work, moving peoples were used and statistical models were extracted out of this, but it's a very artificial approach in detecting a crowd in a real-life scenario. We outperformed the statistical baseline method. We outperformed the SSI signal strength approach. You can see more about this in the paper. And an important thing is to make an accuracy trade-off between the exact people count and the occupancy level. And an interesting conclusion is also that carefully placed directional antennas may result in a measurable increased performance, but not in a significant performance improvement. Thank you.
So now it is open for questions.